6.5 Behavior of accumulation functions. So again, accumulation function is in the form of big uppercase F equals integral from a to x lowercase f of t dt. So everything we're doing today is a review from a lot of things we learned in Unit 5, analyzing the first and second derivative and what it tells you about the behavior of a function. So big F is increasing when the derivative is greater than 0 or positive. Again, a function is increasing when the derivative is greater than 0. Same thing for decreasing, well, vice versa for decreasing. The derivative would be negative, less than 0. You can feel free to pause, try this first column out on your own. Don't worry about the second column. So a function has a relative max when the derivative goes from positive to negative. Function has a relative min when the derivative goes from negative to positive. Concave up when the second derivative is greater than 0. Concave down. Second derivative is negative, less than 0. And there's a point of inflection when f double prime changes sign from negative to positive or positive to negative. So when we have an accumulation function, you have to know the derivative of uppercase f is lowercase f of x. So big F prime is the same as saying lowercase f of x is greater than 0. Same thing here. That's the same thing as big F prime less than 0 is the same as lowercase f is less than 0. And here are all the rest in this column written out. And big F double prime is the same as saying lowercase f single prime of x. Get these all written down. Here's an example problem here. We have the accumulation function g of x is equal integral from a to x f of t, where this graph here is f. We want to find the relative minimum of g. So there's a relative minimum when g prime goes from negative to positive. And if you notice, the derivative of g is f. So this graph says f, that's the same as saying, well, f and g prime are the same thing. So we want to know when g prime, or f, this graph goes from negative to positive. You can see it's this point right here where g prime goes from negative to positive, because g prime is just f. So this is roughly, it's between 5 and 6. We can say x is approximately 5.4. That's the relative min. So now we want to find the relative max. Again, the relative max is when g prime goes from positive to negative. Again, g prime is f. So we're looking at when does this graph go from positive to negative? Well, that happens when x is equal to 3. So now we want to find where the intervals where g is concave up. So when is g double prime greater than 0? Well, the second derivative of g is f prime is greater than 0. So we know f prime is greater than 0 when f is increasing or the slope's positive. So if you see from right here to right here, from 4 to 6, that is when f is increasing or f prime is greater than 0. Now we want to find the intervals where g is concave down. So that is when we want to know when g double prime is less than 0 or f prime is less than 0 or f is decreasing. So from 2 to 4, you see g double prime is less than 0 or f prime is negative or f is decreasing. Points of inflection is when G double prime changes sign. Again, G double prime is F prime. That's when F prime changes signs. F prime changes signs, meaning the function's going from decreasing to increasing or increasing to decreasing. So you can see right at x equals 4, here's the answer. Right before x is equal to 4, you can see f prime or g double prime is negative because the function here is decreasing. Then right after 4, the function is increasing. F prime or g double prime is positive. So that's the point of inflection because that's when g double prime or f prime, in this case, changes sign. This last one here, if g of 1 is equal to 5, so g of 1 is 5, that's our starting point. What is the maximum value of g on the interval 1 to 5? So we're starting at 5, and we're going to add the integral from 1 to 3, because that's all a positive area. 1, 2, 3 of f of t dt. Again, you're starting at 5, and all this space you're accumulating with the function, that's adding on to your value. We're stopping at 3, and we're not doing the integral from like 1 to 5 because after 3, this is all below the x-axis. So your value is decreasing. So we want to stop at the integral from 1 to 3. Ignore everything afterwards. So this right here, this square, that's a 1. This square here, that's a 1. This is a triangle, base times height divided by 2. So it's 1 times 2 divided by 2. That's a 1 as well. So this area underneath the curve from 1 to 3 is just 3. So it's 5 plus 3 is equal to 8. That's your answer. Let g of x equal this function here, where the graph of f is shown on the right. Find the x value where g has a relative maximum. So g has a relative maximum when g prime goes from positive to negative. So let's first find the derivative. G prime of x is equal to f of, you plug the upper bound in, so you instead of the t, you do x over 2 plus 5, and then chain rule. You have to multiply by the derivative of the upper bound. Well, the derivative of x over 2 is just 1/2. Derivative of 5 is 0. And then you want to set this equal to 0. And you can just multiply both sides by 2, so you have a f of x over 2 plus 5 is equal to 0. So if you look at this graph, there's the relative max when g prime goes from positive to negative. Again, g prime is f. So g prime goes from positive to negative at x is equal to 3. This is a max. So what we want to do is when the inside of here is 3, you have a relative max. So you can just set this here equal to 3. X over 2 plus 5 is equal to 3. Subtract 5 on both sides. X over 2 is equal to negative 2. Multiply both sides by 2. X is equal to negative 4. That's it. You can go ahead and get started with the practice.